Hello everyone, I am K. Narsimurthy, working in Government First Aid Women's College, Tumkur. I am going to present a video for the subject physics. This is my 26th video for the Tumkur University students of second semester. So in the second semester, entire syllabus has been divided into 60 sessions. So this is the 26th session video which I am presenting you. So the entire syllabus has been divided into 4 equal parts. Each part is called as an unit. Now this is a second unit, and in the second unit one chapter I finished, that is all about the magnetostatics. That is all about the Biot-Savart's law, Ampere circuit law and its applications. And also I have discussed a very sensitive instrument to measure a sudden flow of charge for a short interval of time, and that was the ballistic galvanometer. So we applied ballistic galvanometer and we found the high resistance by method called leakage. And I discussed many problems regarding the ballistic galvanometer and the magnetostatics in my previous video, which is regarding to this second unit. So this is the 11th video in the second unit and 26th video in the entire syllabus. And I'm going to start a very new chapter here. It is the electromagnetic induction. Right. So I told you in my previous video that Astor in 1820 he discovered a new phenomena which is called the magnetic effect of electric current. It means that when a current carrying conductor produces a magnetic field around it. Current carrying conductor produces a magnetic field around it, and this process or this phenomena is known as the magnetic effect of electric current. It was discovered way back in 1820 by Astor. Very old phenomena. So when we look for the converse effect, suppose if magnetic field can produce an electric current, that converse effect of production of electric current with the help of varying magnetic field was also discovered by the Michael Faraday in the year 1813. Okay, the magnetic effect of electric current was discovered by Astor in 1820. After 11 years after that, a converse process was discovered by Michael Faraday, and it was in 1831. It means to say a current is produced by this varying magnetic field. We'll see in detail how the current is produced with varying magnetic field. So we need to know what is electromagnetic induction is. So it's a phenomenon of EMF and hence the current induced in the coil due to the change in the magnetic flux linked with it is called electromagnetic induction. See, the thing happening here is the magnetic flux linked with the coil changes. What do you mean by magnetic flux? The number of lines of forces, number of magnetic lines of forces crossing that area normally is what the magnetic flux is. That magnetic flux will keep on changing. The magnetic flux linked with the coil means the number of magnetic lines of forces passing through the coil will keep on changing. If it is keep on changing, certainly an EMF is induced in the coil. A current is induced in the coil. This phenomena, this process is known as electromagnetic induction. The name itself says that there is some induction here, there is something which is induced here. It is from the magnetic field, it is from the changing magnetic field. What actually is induced is the current or the EMF in the coil. Okay, so this is what known as the phenomena known as electromagnetic induction. I'll repeat this the definition. It's a phenomenon of EMF or a current induced in the coil due to the change in magnetic flux linked with the coil. The important point here is the change in the magnetic flux. If there is no change in the magnetic flux, you cannot expect any induced voltage or any induced current, right? So that's okay. The next thing is the EMF induced in the coil is due to the change in the flux, which is called induced EMF. The EMF which is induced in the coil is called as induced EMF, and the current induced is called as induced current. Now we have two things. One is induced EMF and another one is induced current. Why it is called induced EMF? Because it is induced because of change in magnetic flux linked with the coil. So that is why these two things are called induced EMF and this is called induced current. Okay. Right, we have a very famous experiment. You might have studied this experiment in the second PUC while studying this electromagnetic induction. Students, you have a same chapter in the second PUC, same electromagnetic induction chapter in the second PUC, and the basic things you all know. It is all known thing. This Coil-Magnet experiment, or it may be the Coil-Coil experiment. These things are very well known in the second PUC, but it's a glance of the whole thing which is known, so that I can extend this. I can extend this to a self-inductance and the mutual inductance. For that, you need to clearly know the background of this. I mean, you should know what is actually the Faraday's laws is. Yes. Before going to the Faraday's laws, you need to know what is actually the Coil-Magnet experiment. Now, we have considered a coil C. Look at the diagram. You have a coil which is called C, and this coil C is connected to a galvanometer. You might have seen the galvanometer in the laboratory. It's a small box. Center you can find a 0. You will have a deflection in the right side as well as in the left side. So the needle of the galvanometer can move right or it can move left also. Okay, right, we have connected a galvanometer to the coil and we have a bar magnet, and the bar magnet with north and south pole. You know, magnet will have two poles, one is north pole and another one is south pole. Now this magnet is moving towards and away from the coil as shown in the figure. What I am doing here is I am just moving the magnet towards the coil, and I am moving the magnet away from the coil, and look at what is actually happening in the coil and what galvanometer shows. Suppose the first observation I can make out here is when a bar magnet is moved towards the coil, means the north pole of the magnet is moved towards the coil, the galvanometer shows deflection in one direction. If galvanometer shows deflection, means it is saying that there is some current flowing in the circuit. So there is some current flowing in the coil. There is some current induced in the coil because of the motion of the magnet. When a magnet is moved away from the coil, the galvanometer shows deflection in opposite direction. Okay, did you got the point? When the magnet moved towards the coil, the galvanometer shows deflection in one direction. If it moves away from the coil, it shows deflection in another direction. Okay, it means to say that if you move towards a coil, current flows in one direction. If you move the magnet away from the coil, current is reversed. Current is moving in the opposite direction. Okay, yeah, this indicates that current is induced in the coil. If there is a deflection in the galvanometer, this shows that there is some current in the circuit. It means to say there is some current in the galvanometer. Now the current is induced in the coil because the galvanometer is showing the deflection. Right, some more observation we can make out here is a similar results are observed when the coil is moved by keeping the magnet at rest. Dear student, the thing which you need to observe here is now the magnet is at rest. I am moving the coil towards or away from the magnet. Magnet is kept rest now. Magnet is rest. Magnet is fixed. Now what I am doing is I am just moving the coil. Even if you move the coil, the same thing has been observed. Same thing in the sense, there is the galvanometer shows the deflection in one direction when you move a coil towards the magnet. When you move a coil away from the magnet, galvanometer shows deflection in the opposite direction, which clearly shows that there is some current flowing in the coil when you move a coil towards or away from the magnet. Okay, right. Another observation is, it is found that the induced EMF and the current is large when the magnets or coil move faster. Suppose what I am doing is, if I move faster, if I move the magnet or if I move the coil, anything you move, if you move a coil faster, you can see a large current induced in the coil. Okay, so the current depends on how fast you are moving the magnet or a coil. Okay, so right, finally I can say that if there is any relative motion between the magnet and the coil, there induces a current in the coil. You should make a note here, there must be some relative motion. You understand what is actually the relative motion? If both coil and magnet move with the same velocity, it is not a relative motion. If they are moving together with the same velocity in one direction, it is not a relative motion. If one is moving towards or away, another one is at rest, it is a relative motion. If other one is at rest and the one which is moving towards or away, this is a relative motion. If there is no such relative motion between the coil and the magnet, the galvanometer does not shows any deflection. You cannot expect any EMF or current to be induced in the coil. Okay, so overall I can say that if there is any relative motion between the coil and the magnet, there induces an EMF and current flows through the coil, which is shown by the galvanometer deflection. Right, that was the conclusion we can make out here is, an EMF or a current is induced in a coil only when there is the change in the magnetic flux linked with the coil. Be careful, this word makes very good sense here. Change in the magnetic flux. What is actually changing if you move a magnet or if you move a coil? If you move a magnet, it is the flux which is linked with the coil is actually changing. Even if you move a coil towards or away from the magnet, it is the flux which is actually linked with the coil was changing. So overall I can conclude that if flux changes, if magnetic lines of forces changes, then only there is an EMF induced in the coil. That is what the conclusion you have to make out here. It is not a simply movement of magnet or a movement of the coil. It is the flux which is actually changing by all this mechanism, by all these movements. Whatever the movements which you are making to produce a current is just because of the flux which is actually changing, which is linked with the coil. So that is why an EMF or a current is induced in the coil. That is why the galvanometer shows deflection. As long as the flux changes, galvanometer will keep on showing the deflection. When once the flux changing of flux is stopped, the galvanometer will not show any deflection. You cannot expect any current in the coil. Okay, right. When you have to observe one thing here is, if flux is constant, then only you cannot expect any induced current or a induced EMF. You need to have a change in flux to get an EMF induced or a current induced in the coil. Right, we move on to the next thing. Yeah, this is one experiment. Again, these are all the experiment which gives us the Faraday's law. This is a coil-coil experiment. This is not a coil and magnet. Now we have two coils. So one coil C1 is connected to a galvanometer. Another coil C2 is connected to a battery. This coil C2 carries a steady current because it is connected to a battery. When the current flows through the coil, as you know, it is a magnet. With the magnetic effect of electric current, it produces a magnetic field around it. So coil C2 is producing a magnetic field. The coil C2 is what producing a magnetic flux. Right. So when coil C2 moves towards the coil C1, coil C2 which is producing a magnetic field, if that moves towards the coil C1, the galvanometer shows deflection in one direction. When coil C2 moves away from the coil C1, galvanometer shows deflection in the opposite direction. Exactly what's happened in the previous experiment, which was Coil-Magnet experiment, the same thing was happening with the Coil-Coil experiment. Okay, so if C2 moves towards C1, then the galvanometer which is connected to C1 shows the deflection in one direction. If C2 moves away from C1, then also the galvanometer which is connected to C1 shows the deflection in opposite direction, which clearly says that some current is induced in the coil C1. Okay, I am moving C2 towards or away from the C1, and there is a current induced in C1. Right. Similar results are observed when coil C2 is fixed and C1 is moved towards or away from C2. If the first coil is moved towards or away from C1, then also you can get the deflection in the galvanometer. When you move C1 towards C2, galvanometer shows deflection in one direction. If you move away from this C2, then the galvanometer shows the deflection in opposite direction. Now it is found that the current is produced even if you move C2 or even if you move C1. Okay. Now one thing which we can observe is the current is large. The induced current is large when the coil C1 or coil C2 move faster. If your movement is faster, you can expect more current to be induced. Okay, right. So finally I can say that if there is any relative motion between these two coils C1 and C2, if there is any relative motion between the two coils, then only the current is induced in the coil, then only the EMF is induced in the coil, then only the flux which is linked with the coil changes. Suppose if there is no relative motion, if they are moving together like this, then you cannot expect the galvanometer to show the deflection. There is no relative motion, you cannot expect any EMF or the current to be induced in the coil. Okay, so one thing is the current or EMF is induced only when there is a relative motion between the two coils. I can say that the current or EMF is induced in the coil only when there is a change in the magnetic flux linked with the coil. So very clear from this experiment also that the current is induced in the coil only when there is a change in the magnetic flux linked with the coil. So deflection exists as long as this coil C1 or C2 both are in a relative motion. If relative motion once ceases, then you cannot expect any current, any deflection in the galvanometer. That was the result. Same results I am getting in the first experiment, the same old result I am getting here also. It clearly says that if there is a change in the flux, definitely there is some EMF or a current induced in the coil. Yeah. We move on to the next experiment, which is again the Coil-Coil experiment. Okay. So consider C1 and C2 placed very close to each other, and the coil C1 is connected to galvanometer, coil C2 is connected to battery with a tap key. This time we have a plug key. Only change which is made here is plug key. It's a second experiment, Coil-Coil experiment number 2. Only change is the plug key is introduced here. We'll see what is the observation we can make with this. When plug key is pressed, galvanometer shows deflection in some other coil. Look at these two. Okay. So coil C2 is connected to battery and plug key. If I press the plug key in the which is connected to the coil C2, the galvanometer in the coil C1 shows the deflection. Okay, very magical thing here. If you press this plug key, here this galvanometer shows the deflection. Okay, yeah. When plug key is removed, the galvanometer shows deflection in opposite direction. That is also one thing. You Put a plug key, you can expect deflection in one direction. If you remove the plug key, you can expect a deflection in another direction. Be careful, it is in the coil C1. I am passing the current in coil C2 by pressing the plug key K, and the EMF is induced in the coil C1, the other coil. If the plug key is pressed continuously, what happens? If you keep on pressing it, then the current flows, same current flows in the coil, same magnetic lines. There won't be any change in the magnetic lines. Beginning you can expect a current. After that, the galvanometer does not show any deflection. So that means, that's clearly stated that when you are not changing the flux, you cannot expect any current, any induced current or any induced EMF. Similar results are observed when current in the coil is increased or decreased. And that's what we are doing. When you press the plug key, current is increased. When you remove the plug key, current will be decreased. Okay, the same thing which we have observed. The results of this coil-coil experiment 2 is an EMF or a current is induced in the coil only when there is a change in the magnetic flux linked with the coil. The same result. I am getting the same result from all these three experiments. This experiment also indicates that again there is a relative motion between the two coils. Is not absolutely required to induce an EMF or current in a coil. Oh, this is a one different conclusion I can make out here. What actually this was, even there is no relative motion, you can expect some current. How it is? Because here I am increasing the current and decreasing the current. I am not moving the coil 2 towards coil C1. I am not moving the coils. I am not making any relative motion. What I am exactly doing is, I am just increasing the current and decreasing the current. Even you increase the current, the flux which is linked with the coil C1 will change. So finally what I want is the flux to be changed to induce an EMF. So that is what exactly I am doing here. I am changing the flux. How I am changing the flux? By increasing and decreasing the current in the coil 2. By increasing the current, the flux linked with the coil C1 changes, EMF is induced. If I decrease the current, the flux which is linked with the coil C1 will change, therefore an EMF is induced. You can change the flux by any means for that matter, either by moving the coil, either by doing a relative motion, or by increasing or decreasing the current. Whatever the way you do, you just change the flux which is linked with the coil, then exactly the EMF or a current is induced in the coil. That is what this electromagnetic induction is. Okay. Right, now after understanding all these three experiment 1 which is Coil-Magnet experiment, experiment 2 is Coil-Coil experiment, experiment 3 it was again the Coil-Coil experiment, that was by increasing and decreasing the current. Now we will see what is the Faraday's law of electromagnetic induction is. The first law says that whenever there is a change in the magnetic flux linked with the circuit, an EMF and hence the current is induced in the circuit. So induced EMF exists as long as there is a change in the magnetic flux linked with the circuit. Okay, this is all known. The experiment result will clearly says this itself. Okay, when there is a change in the magnetic flux linked with the coil, then an EMF is induced in the coil. The induced EMF exists as long as the flux linked with the coil changes. Okay, when the change in the flux stops, when change in the flux ceases, then the current will not induced in the coil. The current induced will stop and you cannot have any current in the coil. Now we'll move on to the second Faraday's law. This second Faraday's law says that the induced EMF is directly proportional to the change in the magnetic flux linked with the circuit. Okay, so if change is more, EMF induced is more. If change in the flux is less, the EMF induced is also less. Okay, so overall I can say the magnitude of induced EMF is directly proportional to the change in the magnetic flux linked with the circuit. So I can write an equation. If E is the induced EMF in the circuit due to the change in the magnetic flux, then E is directly proportional to d phi by dt. d phi by dt is what the rate of change of magnetic flux. Right. If this is what the Faraday's second law is. The Faraday's law, one drawback here from the Faraday's law is it does not give any idea about the direction of the current which is induced. But Lenz's law gives the direction of induced current. We will see the Lenz's law and we will understand how to get a direction of induced EMF. So it states that the direction of induced current is such that it opposes the cause which is producing it. Okay. Now you understand that the direction of current which is induced in the circuit is like that. It opposes the cause which is producing it. What is actually the cause which is producing it? The flux change. So the current is flowing in such a way that it opposes the change in the flux. So current should oppose the change in the flux. In such a way the current flows in the circuit. In such a direction the current flows in the circuit. Yeah, now we know that E is minus d phi by dt because minus d phi by dt was the change in the flux. The E will always oppose the change in the flux. So therefore it is minus d phi by dt. Now I can make an illustration with these examples. Consider coil with end phases A and B. We have two end phases A and B connected to a sensitive galvanometer G, which as shown in the figure. When the magnet is moved towards or away from the coil, again the flux linked with the coil changes and hence the current is induced in the coil in a direction which opposes the motion of the magnet. Yeah, as I told you, as Lenz's law says that the current is induced in that direction, it should oppose the change in the magnetic flux. It should oppose the motion of the magnet. Okay, the current is induced in such a direction that it should oppose the motion of the magnet. Now north pole of the magnet is moving towards the coil, so that now the current is in such a direction that it should oppose the movement of the north pole towards the coil. How it will oppose? How it will oppose? So it can oppose by producing the north pole here. If north pole is coming means if you produce a north pole, it is opposing it because we know very well that the like poles repel each other. So north pole is coming towards. If you put a north pole here, it will oppose us. So current should flow in such a direction in the coil that it produces a north pole. How north pole is produced in the coil? If a current flows in an anti-clockwise direction, then the phase of the coil behaves like a north pole. We know this phenomenon. Anti-clockwise will produce a north pole, clockwise current will produce a south pole. So north is coming towards a coil, it should produce a north pole because it should oppose the movement of this magnetic north pole towards the coil. Right. So further, if north pole of the magnet is towards the coil, the work has to be done against the force of repulsion of the north pole of the coil. Now, if you want further to move this, so the current is produced, north pole is produced in the coil, so we have a north pole, you still want to move the north pole towards the coil because it is opposing it. So if you want to move it, you need to do some work. Work has to be done to move this magnet against the force of repulsion of the north pole which is produced in the coil. You need to do the work done. Suppose the similar way, if a coil north pole is moving away from the magnet, what should be the pole which is generated here? It should oppose this motion. It should oppose the motion of this. Now it should produce a south pole. South pole is what it opposes the motion of a north pole away from this coil. So how the south pole is produced? If current is induced in the coil in a clockwise direction, the phase of the coil behaves like a south pole. It produces a south pole. So yeah, if you want further if you want to move a north pole away, you need to do the work done against the force of attraction of this south pole. Now it starts attracting, you need to move away, you need to do the work now. In both the cases, work has to be done in moving the magnet. For the first time it is moving against the repulsion, second time it is moving against the attractive force. Now mechanical work is stored as an energy, electrical energy in the coil. That's what the current is induced in the coil. So whatever the force you are applying, whatever the work you are doing to move the magnet towards or away from the coil is what stored as an electrical energy in the coil. Thus direction of induced current is such that it opposes the cause for its production. Hence the Lenz's law is in accordance with the law of conservation of energy. So it is very clear that if you move a magnet, it's keep on producing the current. No, it never happens. Once you move a magnet, this current in the coil will keep on producing the current. It cannot happen. Okay, it is against to the law of conservation of energy. Therefore, the current which is produced here should oppose the movement of the magnet. If you want further, if you want to move this north pole towards it, you need to apply the force. You need to do the work. And that work is stored as electrical energy in the coil. Okay, so this is in accordance with the law of conservation of any law for that matter. It has to be in accordance with the law of conservation of energy. Any law for that matter cannot violate the law of conservation of energy, which says that the energy neither be created nor be destroyed, but it can be converted into one form to another form. So energy is not continuously produced without any help. Okay, right. These are the very famous laws in the electromagnetic inductions. I have discussed the two important laws. One is Faraday's first law, another one is Faraday's second law, another one is the Lenz law, which gives the direction of induced current. Okay, these are the three important laws in the electromagnetic inductions, which subsequently use in many derivations which regarding to the electromagnetic inductions. Thank you very much.